Okay, so this is the factors that affect Kp. And just a little heads up, it's basically the same as the factors that affect Kc. Let's go into the detail. I'm just going to set up my page here. So let's say we've got a nice and easy reversible reaction where 1 mole of reactant gases goes to 2 moles of product gases. And of course, if we did our Kp expression, that would be Kp equals the partial pressure of the products squared raised to the power of their molar ratio divided by the partial pressure of the reactants. And just notice I'm using curly brackets, not square brackets, as square brackets would mean concentration. So that would be Kc, we are talking about Kp. And rather than talking about partial pressure of the product squared, I'm just going to refer to that as the top term. Now we do have a fancy maths word for that, which is the numerator. Or I could talk about my bottom terms there, which would be the denominator. I'm mostly going to talk about top and bottom, but you might also see these fancy numerator and denominator used around the place as well. So let's have a look what happens then. If I was to increase the pressure, what I would be doing is increasing the partial pressure of both my product and my reacting gases. So when you increase the pressure, the partial pressure of all your gases increases. However, as I've got this squared here, basically as there's more moles of gas on the right here, what's going to happen is my top term, or my numerator, will increase more. Both of these will increase, the top and the bottom, but the top term will increase more because of that squared there. So let's get that down in our little skeleton answer here. So when we increase the pressure, the top, or the numerator, in the Kp expression increases more than the bottom term or the denominator. Okay, so what's that going to do to the position of equilibrium? Well, thinking about Le Chatelier's principle, if we was to increase this side, the position of equilibrium would shift to the left to try and reduce that change. So let's get that down. The position of equilibrium shifts left. But what's going to happen when the position of equilibrium shifts left? Well, your products are going to change into reactants, and so the partial pressure of your products will go down and the partial pressure of your reactants will increase. And so now what's going to happen is our bottom term will start becoming bigger compared to our top. This is all a comparison. Let's get that down. The bottom of the denominator in the Kp expression increases more than the top or the numerator. So if you look at what's happened by the end of the day, these two effects are going to cancel each other out. And so Kp will be restored. You have restored Kp. You've increased your top partial pressure, or your numerator, but you've also increased the denominator as well. So by the time equilibrium has been re-established, Kp will be the same as before because you've just increased the top and the bottom in a proportional way. Okay, so Kp is boss. Pressure cannot affect Kp. Let's have a look at temperature though, and let's just assume that our forward reaction is endothermic. So this would have a positive delta H. Well, if we increase the temperature, let's think about Le Chatelier's principle. If I increase the temperature, the position of equilibrium will shift in the direction of the endothermic reaction to try and bring the temperature back down, which in this case is to the right. So in my example, the position of equilibrium shifts right. Now let me just get rid of these arrows from before, so they're not there anymore. Now, if the position of equilibrium shifts to the right, then overall your reactants are going to be changing into products. And so your top term, your numerator, will increase more than the bottom term. So top or numerator increases more, in this example, than the bottom or the denominator. Now, if we increase the top term more than the bottom term because of math, that means our final answer will increase. So I'm kind of running out of space here. So therefore, in this example, Kp increases. So like Kc, Kp is boss apart from temperature. If you start fiddling around with the pressure, by the end of the day, when you've re-established equilibrium, both your top and your bottom term have increased proportionally, and so Kp is restored. Whereas when you increase the temperature, you're only going to increase one of those terms, the top or the bottom, more than the other, and so Kp will change.